So I'm really excited to be here and to be able to help celebrate the discovery 50 years ago of quasars. I'm one of those people who was attracted to astrophysics by quasars. I remember writing a term paper when I was in college, and I found it the other day. I found it it was about 2 years ago. I was cleaning out my mother's house, and I found this term paper, quasars, typed on a typewriter. Those are machines that came before computers. It was an electric typewriter, though, so I'm not as old as some people might think. Okay. And when I was in graduate school, when I was writing the term paper, I read every paper I could find on quasars. There weren't that many, actually. You could actually read the full literature as a college student. That's not possible even on a daily Astro PH, probably. Later, as a graduate student, I used this V over VM technique to estimate luminosity function of BLAC objects, which was a paper I read of Maarten Schmidt. So I, of course, knew his work. I hadn't met him, and I was at some meeting, and he was very charming and kind and asked me a question, which I actually could answer. So I thought that was really wonderful. Anyway, so I'm really pleased to be helping to celebrate his discovery and the work of so many people. And I thought before I came here, I better consult the Oracle because I don't know him well. So I went on the computer, I Googled him, and I found this interview, 50-year cosmic mystery, 10 quasar questions for discoverer Maarten Schmidt. And as a backdrop, I have to say, I was doing my PhD thesis on AGN, BLAC objects, Blazars, at about the time that it was becoming less interesting to everyone else. And so, you're kind of in this growing ghetto, whatever. So I was very heartened to see that the first question had to do with how important is the discovery of quasars. And Professor Schmidt said that it was really important because it involved black holes, and apparently they were accreting material. So I felt good about that. Okay, the thing I've been doing is interesting. So I have to mention that as they accrete material, they also make jets, and jets are integral to the discussion of Blazars. So I'll be talking about jets, as Roger mentioned. Another thing he pointed out was that when you looked at the statistics, there's a strong evolution in the number density of quasars, 100 times more in the past than now. And I was really excited about that because I've worked on number densities, and I'm going to talk to you about Blazar demographics. So I was really feeling good. I'm in a good field. I have done some interesting things, and unfortunately I read on. so then they asked him this question. How do you feel about the current state of the field? Have we made a lot of progress toward understanding quasars in the past half century? And Professor Schmidt said this. The understanding has not developed very much in these last 50 years. So, okay, well, thank God we don't all need external validation. We can just soldier on ourselves. Okay, so I'm going to tell you about Blazars in particular. This, of course, is a cartoon that is not meant to be realistic, but some fraction of active galaxies and quasars have jets. Maybe all of them do, but very few are high-powered and are in galaxies that they can punch through and actually make large-scale, powerful radio jets. When that happens, of course, they must be randomly oriented on the sky because we don't live in a preferred region, or at least we didn't when the Scopes trial took place. Maybe we do now. So a few of them will be pointing at us. And when they are pointed at us, and these jets, I should have mentioned, are moving, the particles have a bulk motion outward that's nearly at the speed of light, very high fraction of the speed of light. And so not only are they you in a location to see them, but they are actually magnified by many orders of magnitude. They are by a special relativity effect. When I was a college student and I took freshman physics, probably like many of you, since the curriculum hasn't changed in 100 years, you learned about special relativity. And I don't know about you, but I thought it was a total joke. I mean, I could work the problems, and I knew one twin got older than the other, and I knew, this clock said that, and that clock said that, but I didn't believe it existed. And then when I was a graduate student analyzing X-ray data of BLAC objects, which we didn't know were BLAC objects, but we figured it out, and then proving that you could only explain their spectral energy distributions if there was bulk relativistic motion outward. It was like a revelation. Maybe everybody has this revelation in physics, but the stuff you think is fiction turns out the universe does it. So that was very exciting. And blazars are these things that we're looking at the jets end on. They are highly magnified, and therefore they're great laboratories for studying jet physics. So through the talk, I'm going to sort of give you this laundry list of what we know. We proved that about the time I was doing my thesis, we proved that blazars had to be relativistic jets pointing at us. This was disturbing to many people because, of course, they can't know about where the Earth is, so there must be many more objects pointed elsewhere, and I'll talk about that in a minute. If you want to study the physics of the jet, then nature has done this very nice thing of magnifying its emission for you tremendously. So looking at blazars is a way of studying the particle density and energy in these jets, in the magnetic fields. I'm not going to say a huge amount about that. I was leaving that to Roger to explain everything. So let me talk a little bit about demographics. Early on, one of the objections was that we see so many blazars. In those days, it was of order 100, which seemed like a lot at the time. That this idea of them being beamed was perhaps uncomfortable to some people because they said you have to have 1 million more objects that are not pointed at us. Then we realize, of course, that you have this selection effect because they're beamed at you and so much brighter. Of course, you're more likely to see them to large distances than you are to see their parent population. And so let me mention what the potential parent population was radio galaxies, and they come in 2 flavors. Phaneroff-Riley 1, which is morphologies like this one, M87, where the jet is not so powerful, and it sort of peters out after a while, and you get large amounts of diffuse emission. The one-sided jet means it's relativistic, and the one that's going away you don't see because it's beaming to some other astronomers in some other part of the universe. But this jet is not so energetic. And then the more energetic classic jet is, of course, Cygnus A, where you can barely see the jets. In this beautiful picture, you actually can see both of them, but they're beaming their radiation, in the plane of the board, if you like, over there, not to us. So the jets look faint, but you can tell how intrinsically luminous they are by the amount of energy they're depositing in the lobes. I should tell another story. Fraser Owen's not here, but when I was writing the review paper on Radio Loud AGN, I asked him for some images of FR1s and FR2s. I wanted an FR1 and FR2 to put in the paper. And he sent me 3 images. If he had sent me 2, I could have passed the quiz because, you can always tell which one is more FR1-like than the other one. But he sent me 3, and I couldn't tell what they were. So I tell you that to say that these beautiful examples that are the classic FR1, FR2, many radio galaxies don't look that clean. Okay, so numerically, you want to compare the FR1 radio galaxies, that is the low-power jets, to the lower-powered blazars, which are the BL-lac objects. These are generally lineless, and in particular, the low-power ones are the high-frequency peak ones. I'll show you what that means in a moment. And then the powerful ones are the flat-spectrum radio quasars. So in order to do this, you have to think about what beaming does to the distribution of luminosities you see. So I'm showing you actually some very old work, but it actually is still valid, happily. If you had just, say, one luminosity of jet, and all the luminosity is in the jet, and you say, okay, let me take an ensemble of those and randomly orient them on the sky, what would I see? What you would see is a very flat distribution, like this, which is basically dictated by the probability that you get a certain angle. Okay? So I've lost the pointer, which I usually don't like to use, so I'll use my arrow. Over here at the highest luminosity is the maximum beaming, so that's the one pointing at you. And over here at the lowest luminosity, that's the one pointing away from you. And then this flat slope is just dictated by the probability of getting a particular angle. Okay, so if you had some other luminosity and you beamed it, it would look like that, and a third one would look like that. And now you can see that if you had an intrinsic luminosity function that was steep, your beamed luminosity function would be the sum of those other things, so it looked like that. Okay? So the beam luminosity function is a broken power law with a very flat slope. And then all the objects on this steep part are maximally beamed. So the blazars are kind of out here. Okay. Now, of course, you have to do a better job because there isn't one Lorentz factor. You have other emissions besides a beam jet, et cetera. But we did that. And we compared to populations. I'm just going to show you one of them. This is the luminosity function, the X-ray luminosity function of FR1 galaxies and BL-LAC objects. So the blue dashed line is the luminosity function of FR1 galaxies. I haven't showed the data because I don't want the figure to be too cluttered. And then the purple dashed line is basically the fit to the blazars, taking evolution into account. And you can see that it fits. It may not convince you that it has to be correct, but I have to explain that at the time, people were thinking there weren't anywhere near enough radio galaxies. So the picture I want you to get from here is that the BL-LACs way outnumber the radio galaxies because they're beamed. Okay? All right. So we did this in the radio. We did it in the optical. In some cases, there weren't much data. There weren't many data. So, yeah. One of the luminosity functions in my thesis, which I won't tell you which one, had 5 objects in it. It was the best you could do in those days. Okay. In the meantime, there's been a very large effort to monitor the emission from blazars. They have, let me show you a spectral energy distribution. This is a sort of a typical spectral energy distribution in nu versus frequency from radio, millimeter, far infrared, all the way up through GeV, and this plot doesn't have the TeV because this object is a GeV emitter. But you can see the characteristic sort of two-humped spectrum. So this first bump here is the synchrotron emission. Everybody's pretty comfortable with that interpretation, including because of polarization. So this is synchrotron emission. And then there's a high-energy component that we didn't know before the Egret satellite launched. There were a few predictions there might be gamma rays, but nobody knew that. And it was a little disconcerting because, of course, all the energy is coming out in the gamma ray. So our previous estimates of energy were a little off. But the second component, there were a number of competing models for it. In general, it's more luminous and more variable than the synchrotron component, particularly in these luminous quasars like the 3C279. And there were essentially 2 winning hypotheses. One, that the same electrons that made your synchrotron emission were upscattering ambient photons. And the other, that there is instead some primary acceleration of protons that then decay eventually into electrons that radiate the high-energy component. And those were the 2 models in competition before the launch of the Fermi satellite. I think Fermi has settled this question. This is just a picture of the Fermi gamma ray sky. It's a little different from the Egret picture because 3C279, which used to be super bright, and I think, this is so embarrassing that I don't really know, I think it should be somewhere up here, lost the title to this object. This is 3C454.3, which was the brightest blazar in the sky when Fermi launched. So we had a program at Yale to monitor the optical infrared emission from the brightest blazars, the ones that Fermi had put on its watch list. And of course, we were already looking at 3C454.3. And here are the data we got the first season. This is about a few months of data. And what you see sequentially are the gamma ray light curves, UV from SWIFT, and 2 of our 5 smarts bands, a B band and a J band. And I hope you can see that the variations are very well correlated. So you see 2 peaks here in the gamma ray, up, down, and you see the same thing in the lower energy radiation. Now, you cannot do that without a lot of hand-waving. You cannot do that in the hadronic models because there's no reason for a tight, small lag correlation between the radiation. It naturally points to the leptonic models where electrons are doing both the synchrotron radiation and the upscattering to gamma rays. This was actually the first paper on blazars using Fermi data that was published. And just to show you, this is 2 years of data on 3C454.3, where all I've done is overplot the gamma ray light curve in black with the infrared data in red. They're not perfectly correlated, and maybe I can say why in a minute. They're not exactly the same electrons, but they track each other very well. And this is the idea: is you have a distribution of electrons which are governing the radiation that we see. I should have said this is all work Erin Bonning did when she was at Yale. Okay, so we know that the gamma rays are produced by some kind of scattering. I didn't say, but should have said that there are a lot of photons around. At a minimum, there are the synchrotron photons. So every source has synchrotron self-Compton emission. But in the luminous quasars, there's plenty of accretion disk photons and broadline photons, and those are, the energy density in those is much higher, so those are what gets scattered to the GeV, and that's why the GeV gamma rays are much brighter. Okay, so now let's talk about demographics and SEDs again. So this is a compilation of spectral energy distributions of blazars using the egret detected sample. Put together by Fossati. This is a famous diagram now. You see the classic two-humped spectrum, synchrotron radiation, and we now know inverse Compton radiation. And I hope you can see the clear trend. Okay, these are sorted in radioluminosity. As you go up in radioluminosity, the synchrotron peak shifts down in energy. That means the mean energy of the electrons is lower. And similarly, the gamma ray peak, which is at TeV energies for the lowest luminosity blazars, shifts down to GeV energies for the highest luminosity ones. And this is well explained if the electrons are cooling. When they scatter the ambient photons, they cool, and since the quasars have lots more ambient photons from the disk and from the broadlines and so on, the electrons cool more and the peaks are at lower energy. So this was well explained. And I should say that the data from, this is now Fermi data on a similar thing, the gamma ray spectral index versus the peak energy of the synchrotron component. And you see exactly the same trend. The steep gamma ray spectra, that is to say they peak lower in energy, have lower energy synchrotron peaks. So the same trends are seen in much larger samples in the Fermi data. And this was a trend actually first seen by Rita Sambruna, and then Fossati put together his diagram. Now, people criticized this interpretation because, especially with the egret samples, there were a lot of selection effects. These sources there were not many observed. You typically only saw them when they got bright, then they fell below your detection limit. And so the Fermi data have really allowed us to improve our understanding. And I don't have time to walk you through the calculation, but work done with a former undergraduate, Tim Brandt, who's now finishing at Princeton, working on exoplanets. He changed his field. No, it's a great field. But anyway, he's a really smart guy. You should keep an eye out for him. And then a current graduate student, Pei-Wan Mao. We've been doing this work on the demographics of blazars, and we have proved, this is not yet published, that you must have a link between the shape of the spectral energy distribution and the luminosity, exactly as the Fossati picture implies. If you do not have that link, then simulations produce samples filled with objects we don't see. So it's very clean. It's not a selection effect. And furthermore, and here's, maybe this is a way to say it. No, I'll say this later. Okay, this is now the same kind of diagram, but with lots and lots more blazars because they're all detected by Fermi. This was given to me by Laura Morosky, but we have a similar diagram we're trying to finish up now. And the last topic I want to say is that it is actually something of an embarrassing conundrum that's existed for almost 20 years. Which is to say the number density of these low luminosity blazars vis-a-vis the high luminosity blazars. So early on, Laura Morosky and company, and I guess I'm in that camp, talked about X-ray selection of blazars being fairly isotropic compared to the beamed radio. And therefore, the fact that we saw many more of the low power ones in X-rays than the high power ones meant low power was common, high power is rare. So steep luminosity function for jets. Okay? And that's kind of you know, this is kind of what we see in many places in nature. But a few years later, Paolo Giomi and Paolo Padovani took an alternate extrapolation of the limited data and decided the exact opposite. So they said radio selection is unbiased, and when I look at a radio sample, I see mostly these radioluminous things, and therefore they must be more common. And I only see 2 low luminosity BLACs in the radio samples, and they must be very rare. So they suggested the luminosity function looks like this. And for the next 15 years or so, I would say this debate is an open question. So now we have looked at this problem again, and maybe one way to say it is with the previous picture. Yeah. What we were looking at before was the mountaintops, just the brightest few examples of each kind of blazar. As you push down in sensitivity, so you're more sensitive, your samples are larger, you're sampling a larger fraction of the population, you should get closer to reality, okay? And you can sort of already see by eye from this figure, this is Fermi as compared to the simpler figure from Egret. So many more objects, and there are many, many more BLAC objects. They are a much higher fraction of the Fermi blazars than they were of the Egret blazars. So if you don't like that thought, I'll just show you the next. Yeah. So we have redone, we have linked the SED shape to the luminosity, used well-known luminosity functions of blazars and positive evolution, that means more blazars in the past, and simulated the universe and sampled it at the flux limits of existing surveys, so we have constraints. And we find, in fact, that you have to have a normal luminosity function. There are more faint, low-power jets than there are high-power jets, and it's very clean. And one other nice thing that comes out of this has to do with the famous V over VM test, coming back to one of Maarten's innovations. If you calculate the average V over VM for a uniformly distributed population, it should be 1/2. And in his famous paper, he found that it was more than 1/2, meaning there are more at large distances than nearby. And you find that's the case when you do a V over VM test for any quasars, including blazars that have these GeV peaks and infrared peaks. But when you did it for the low-power blazars, what are called the high-frequency peak blazars, where the synchrotron peaks in the X-ray, you actually found that V over VM was very much less than 0.5, 0.4, sometimes even less. And this was seen to be very strange. You have differently evolving populations. Years ago, I speculated with Giomi. I was talking to him, and I said, this must be a K-correction effect. He said, no, I've tried it. It doesn't work. But actually, I have to tell you, it does work. Tim Brandt did this about 8 years ago, and we've now verified it with the Fermi sample. And basically, because the X-ray spectrum is steep for the HBLs, because they peak at high energy, so you're looking at the tail of the synchrotron, as they go up in redshift, that just shifts out of your X-ray band. They get much fainter, so you don't see them at high redshift as often as you should. And when we do our simulations, that effect appears. Okay? So with an underlying positive evolution, our measured V over VM naively is less than 0.5. Problem solved. Okay, so we are back to my list of what we know. I think we have learned this in the last 30 years. Blazars have jets pointing at us. We know something about their jet physics. Like a coward, I have not told you all the problems with that and how we don't exactly know the power in the jets yet, but I'm skipping that. We do know the parent populations quite well. I think we know a lot about how particles are accelerated and where. There is a controversy, as Roger just described, about where the gamma rays are actually produced. We know that much of the time they're produced far from the central engine, but it's possible that some flares occur on much smaller scales, and we have a recent result which has me worried that at least some of the flares are produced quite far inside the broadline region. Let's say it that way. And we have to have this, we understand, I think, that the range of spectral energy distributions and why they're that way. It has to do with electron cooling, and everything is kind of a nice, simple story. And I wanted to end with an idea that just came to my mind the other day, that these quasars have a long legacy, not only of 50 years of learning about them, but when particles are accelerated in these magnetic fields, particularly far from the central engine, the low-energy electrons have lifetimes much longer than the Hubble time. So long after everyone in this room is gone, those electrons are still out there radiating. And after another Hubble time, those electrons will still be out there radiating. So I think that's a beautiful legacy that we can celebrate today.
So yesterday we learned how the term quasar came to be and became officially blessed by Chandra. Who came up with the blazar?
Yeah, Blazar. So the term blazar came from the 1978 meeting on BLAC objects, which was just prior to my entering the field. And I wasn't at the meeting, and I've forgotten who it is. Does anyone here remember? Thanks, yeah.
So it was BLAC quasar, but if they reversed it, we would have called them quarks.
Yes, I think there was some thought that Blazar really sounded good. I have to say it's annoying as hell when you use Microsoft Word, because every Blazar gets turned into Blazer.
On a little less frivolous note, I point to students always that quasars could have been discovered in the 1920s, but weren't. They were noticed, but misclassified as variable stars, which illustrates the time domain.
Time domain, and yeah. So we had to wait for radio astronomy in that case. Maarten?
There are a lot of posters outside of that time discovery. Yeah.
We suggest that TV gamma rays may actually be rather interesting because Broderick suggests that they don't just lose energy by producing pairs in a constant cooling, but they might give rise to pairs that have a fundamentally immediate. Do you have any comments on that?
Oh, yeah, no, I don't, actually. It is an interesting idea, I think, and it links to this idea of feedback, which I forgot to mention was the reason AGN actually have become relevant again and people care. But I don't have a particular comment on that. I would say that when we look at AGN, like the other half of my science interest, I've been looking at the growth of black holes and the effect on the host galaxy. And I have to say we see very little sign of feedback in most AGN host galaxies. So it's not a big, for most galaxies, AGN feedback is not a real huge thing.
Meg, when you look at these deep fields in X-rays, there's a dearth of BLX or blazars. And so can you use that more or less as an upper limit in the evolution? Is this that for?
Oh, okay. No, the deep fields are too small. They're much too small. The density of blazars is tiny. And it's not at all surprising we didn't find any in the deep fields. In fact, you don't find many radio-loud objects. Maybe in Cosmos there's some. You don't find radio-loud objects because they're rare. These are just much more rare.